Hey everyone, welcome back. In this video, we will talk about how to estimate and interpret a linear regression line. So we'll start by defining a regression model. What does that mean? When might we use it? We'll also in this video talk a little bit about how to interpret the regression coefficients. What can we learn from them? What can't we learn from them? Finally, we'll talk about the process of least squares estimation. Now, we won't get too deep into the formulas of how to calculate least squares estimators, but we will talk a little bit about where they come from and why they have that particular name. So let's start by defining the linear regression model. The linear regression model is also sometimes referred to as the simple regression model for the fact that it is mathematically the simplest model that we could fit. Essentially, we're fitting a straight line through our data. So we model the relationship between an explanatory variable, here denoted x, and some response variable denoted y with a linear formula. We say that y is equal to beta 0 plus beta 1x plus epsilon. Here, beta 0 represents the intercept term, beta 1 represents the slope of this line, and that extra term, epsilon, is just like in the ANOVA model. It's an error term. Based on our data, we will choose the best line. We'll fit the linear regression model and get something that looks like this. We say that y hat, our predicted value of the response variable y, is equal to beta hat 0 plus beta hat 1 times x. So once we add those hats, we're representing estimated values, be they estimated coefficients like the slope and the intercept, or an estimate for a predicted value. So let's start with an example. We have some researchers who are interested in how the human brain reacts to emotional stimuli. They've designed an experiment to test how they react specifically to watching their partner feel some physical pain. So 16 couples in their mid-20s were recruited that had been either dating for 2 years or married. So we're looking at couples who are in a long-term committed relationship. The way this experiment worked was that the male partner's hand was zapped with an electrode while the female partner watched. What the researchers were looking for here was evidence of an empathetic response. So is the female partner feeling pain in response to watching the male partner be shocked? They measured this feeling of pain as a percentage, or as a fraction, specifically of the fraction of activity in the brain that the woman experienced when she herself was being shocked. They also measured how empathetic the female partner was on an empathy test. So that's the data we have available. So here's our question. Do the women who are scoring higher on that psychological test for empathy have stronger physical reactions in the brain to watching their partner's pain? So let's start with the response and the explanatory variable here. Our explanatory variable might be the level of empathy. A person who is more empathetic might feel more pain versus someone who is less empathetic. Our linear model then looks like this. Y hat I, or our estimated linear model, or our estimated value for y, will be beta 0 plus beta 1 times x. If you prefer to write this in words, we could say that our predicted brain activity is a linear function of empathy. So that's our model. We'd like to know whether or not linear regression is appropriate. So there are a few things that we need to check. First of all, we want to make sure that a linear relationship makes sense. So if we were to plot the data, is there a linear trend between x and y? We might also look at the strength of a relationship like that, such as by using correlation. So empathy here is measured on a scale from 0 to 100. This is an inventory test score on empathy. Brain activity, again, is a fraction of the response when the female partner was shocked. So subject 1 showed about 12% of the brain activity in the region that responds to pain, watching her partner be shocked as she felt when she herself was shocked. Looking at the correlation, it is fairly strong between empathy and brain activity. We have a correlation of about Looking at the data, there may be some concerns in this data. Specifically, I want to draw your attention here. We have someone who is scoring very high on that empathy assessment scale and feeling a very strong level of physical reaction, whereas most of the other subjects in the experiment scored somewhere between about 20 and 65 on the empathy scale. So we definitely have someone who is much more empathetic than the others in the experiment. Okay, so let's talk about how to get this fitted linear regression model. In R, the function we'll use to fit the linear model is LM, LM standing for linear model. The inside of this function looks a lot like functions we've seen before, specifically t.test and ANOVA. Inside, we write that brain activity depends on empathy. Again, you can read this tilde as depends. So our y variable depends on our x variable. Our data set is then called the brain empathy data set. What this does, or what this reports back, are the regression coefficients. So the intercept, that's our estimated beta 0 or beta hat 0. The empathy score, that is our slope. That's our estimated beta hat for x. So we can write that our predicted brain empathy or brain activity, our predicted y, is negative 0.007254 plus 0.006938 times x. That's our model. Now for any value of x, we can make a prediction using this fitted linear model simply by plugging in that value of x. So let's see how this works with a new couple. The female partner scores pretty high on the empathy assessment. She scores an 82. Let's predict her brain activity or her brain response to those shocks that are being given. How would we do that? Well, we'll plug 82 into our regression equation. So we'll calculate 0.006938 times 82 minus 0.007 to get a predicted empathy score. Now, sometimes these predictions are going to be accurate. Sometimes they'll be very close. Sometimes they might be less accurate. The difference between the predicted value and the actual observed value for every data point is something that we'll refer to as the residual, or the error term. So here our error term, or our residual E, is just simply the difference between the predicted value y hat and the actual observed value y. Now, sometimes our model will overpredict, sometimes our model will underpredict. These models are never perfect. So let's take a look at subject 2 in this data set. Subject 2 has an empathy assessment score of 53 and a brain response of 0.392. So let's start by predicting the brain response. We'll plug 53 in, our empathy score, in for x. Once we do that calculation, and here you can see I've actually done it directly in R, we get a predicted activity of 0.36. We predict that for this subject, we'll see about 36% of the brain activity as we saw when she herself was shocked. For our residual, or the difference, the predicted value minus the observed value, we'll take 0.36 minus our actual observation for subject 2 of 0.392, and we get negative 0.03. So overall, our predictions were pretty close for subject number 2. Our predicted value was a little bit low. We underpredicted a little for this subject. Now let's take a look at subject 3. Subject 3 is a little bit more unusual in this study. Subject 3 has a lower empathy score, 41, and a brain response of 0.005. So this indicates that she had almost no brain activity in the area that feels pain when she was watching her partner be shocked. So let's calculate our prediction. Again, plugging 41 in for x, we get a predicted value of 0.277. We very much over-predicted how this subject would react. Our residual is about 0.272. Sometimes these residuals will be quite large, sometimes they will be quite small. The method that we're using to actually come up with the values for our linear equation, so the estimated intercept and the estimated slope, is something called least squares regression. Now, fundamentally, here is how the least squares regression works. Least squares regression chooses the regression line, or chooses those values for the slope and intercept, so that two criteria are satisfied. Our first criteria is that the residuals should sum to 0. So what this does is guarantee that our errors will average out. Some will be negative, some will be positive, but if we calculated the average residual, we would get 0. The second criteria is that the sum of the squared residuals is minimized. So what that means is that we want to choose the model with the smallest squared residuals. Little errors are okay. If we square a little error, we're not going to contribute very much to that sum. But if we make a big error, we square that big error becomes even larger, and it makes that sum of squared errors quite high. So what we'd like to do is really minimize this. Again, this isn't something that I'll ask you to do by hand. The formulas are in your text if you would like to take a look at those, but it is important to know where this phrase least squares comes from. So that's our brief introduction to regression. In the next video, we'll look at how regression works a little bit more in depth and how to evaluate it. See you then.